Before there were stars, before there were galaxies, before there were planets or atoms heavy enough to form anything solid, the universe already existed. It was not empty. It was not silent. And yet, in a way that is difficult to imagine, it was dark. This sounds like a contradiction. The early universe was incredibly bright. In its first moments, it was hotter than any star that would ever exist. Matter and radiation were fused together in a dense, glowing plasma. Light filled everything. There was no night, no shadow, no darkness in the ordinary sense. But that light did not come from stars. There were no suns, no burning spheres of fusion, no structured sources of illumination. The brightness of the early universe was uniform, directionless, like being submerged inside a glowing ocean with no visible horizon. There were no points of contrast, no shapes, no defined objects, just energy and expansion. As the universe expanded, it cooled. Over hundreds of thousands of years, it transitioned from an opaque plasma into something transparent. Electrons combined with protons to form neutral hydrogen atoms. Light was finally able to travel freely through space. That ancient radiation still exists today as the cosmic microwave background, a faint afterglow from a time when the universe first became clear. And then something unexpected happened. The light faded, not instantly, not dramatically, but as expansion continued, radiation stretched, wavelengths grew longer, energy density dropped. The glow that once filled all of space dimmed into darkness. The universe entered a phase known as the cosmic dark ages. There were still particles, there was still matter, there was gravity, but there were no stars, no luminous objects, no structured sources of new light. Imagine a universe filled only with vast clouds of hydrogen and helium drifting through expanding space. No galaxies yet, no constellations, no points in the sky to anchor perception. If an observer could have existed then, they would have seen almost nothing. The cosmos was enormous, cooling, and silent. This period lasted for hundreds of millions of years. Compared to human history, it is incomprehensibly long. Compared to the full age of the universe, it is only an opening chapter. But it is a crucial one, because during this darkness, gravity was quietly shaping the future. Tiny irregularities in density, slight variations left over from the earliest fluctuations of quantum origin, began to grow. Regions that were slightly denser than their surroundings pulled in more matter. The difference amplified. Structure began to emerge from uniformity. There were no stars yet, but the conditions for the first star were forming. The universe was not designed for light. It did not guarantee illumination. The existence of stars was not automatic. It required imbalance. It required collapse. It required gravity to overcome expansion in specific regions. For hundreds of millions of years, nothing burned. No nuclear fusion, no stellar cores, no supernovae. Only cold hydrogen drifting through dark space, slowly gathering in invisible concentrations. The cosmos was waiting, not passively, not consciously, but physically. The ingredients were present, yet something had to tip the balance. Density had to increase enough. Temperatures had to rise enough. Gravity had to win locally, even while expansion continued globally. The first star would not be gentle. It would not resemble our sun. It would not form quietly in a metal-rich cloud shaped by previous generations. It would ignite in a universe that had never seen a star before. Before there was starlight, there was possibility. And in the immense silence of the Dark Ages, gravity was preparing to create the first true source of structured light, a single star that would change the chemical destiny of everything that followed. After the first glow of the early plasma faded and the universe became transparent, a strange quiet settled over everything. Space was no longer a blinding sea of radiation. It had cooled enough for atoms to form. Hydrogen and helium drifted freely through expanding space. Photons traveled unimpeded. And yet, despite this transparency, the cosmos had no stars. This era is called the Cosmic Dark Ages, and the name is not poetic exaggeration. It was truly dark. There were no luminous objects, no galaxies, no planets, no sources of ongoing fusion, only diffuse clouds of neutral hydrogen stretching across unimaginable distances. The universe at this stage was simple in composition but vast in scale. It contained almost nothing except hydrogen, helium, and dark matter. No oxygen, no carbon, no nitrogen, no iron. None of the elements required for planets, chemistry, or life. Those would come later. For now, reality was chemically primitive. Yet this simplicity concealed tension. Dark matter, invisible and non-interacting with light, had already begun forming gravitational scaffolding. Long before ordinary matter collapsed, dark matter gathered into halos, invisible frameworks that would later anchor galaxies. Baryonic matter, the normal matter made of atoms, followed these gravitational wells slowly, accumulating over time. The process was not dramatic. There were no explosions or bright flares marking progress. Gravity worked silently, amplifying tiny density fluctuations left behind from the earliest quantum variations in the inflationary epoch. Regions slightly denser than average pulled in more matter. The denser they became, the stronger their pull. This feedback loop was the first step toward structure. The universe was not uniform. It only appeared that way on large scales. On smaller scales, subtle imbalances were growing. Hydrogen gas drifted toward invisible centers of gravity, compressing slowly. As density increased, temperatures began to rise. But something was missing. In later epochs, star formation is assisted by heavy elements and dust, which help gas cool efficiently and collapse into compact cores. In the Dark Ages, there were no heavy elements. Cooling mechanisms were limited. Hydrogen had to rely on molecular processes that were inefficient compared to modern stellar nurseries. This meant the first stars would not form easily. Gas clouds had to become enormous before collapse could proceed. The gravitational potential had to overcome thermal pressure without the benefit of metals. The first stellar embryos were likely massive, far larger than most stars born today. The universe was preparing something extreme. For hundreds of millions of years, these dark matter halos continued gathering hydrogen. The densest regions grew hotter. Pressure mounted. At the core of certain collapsing clouds, temperature and density crossed a threshold that had never before been reached in cosmic history. And still, from the outside, there was no visible light. Imagine a cosmos filled with invisible scaffolding and cooling hydrogen seas, slowly converging into knots of increasing intensity. No constellations marked the sky. No bright centers illuminated space. If one could have existed as an observer, the night would have been absolute. But within the densest clouds, gravity was pushing matter toward a tipping point. The Dark Ages were not an absence of activity. They were an incubation period. Structure was forming beneath the threshold of visibility. Energy was accumulating in concentrated pockets. The conditions for nuclear ignition were assembling molecule by molecule. The universe was not static, it was gathering itself. And somewhere within one of these massive hydrogen clouds, in a region dense enough to resist expansion and hot enough to approach instability, the first star was about to ignite, ending the Dark Ages and beginning the era of light. During the Dark Ages, the universe appeared calm, but beneath that calm, a competition was unfolding. Expansion pulled space outward in every direction, stretching distances, thinning matter, cooling energy. At the same time, gravity pulled inward wherever mass accumulated. These two forces did not cancel each other. They shaped the future together. On the largest scales, expansion dominated. But locally, in certain regions, gravity began to win. The victory was subtle at first. Tiny fluctuations in density, imprinted in the earliest moments of the universe, created slight differences in gravitational pull. These variations were unimaginably small, fractions of a percent, yet they were enough. In a universe governed by feedback loops, even a small advantage compounds over time. A region slightly denser than average attracts more matter. As it gains matter, it becomes even denser. The pull strengthens, more matter falls inward. Dark matter led this process. It does not interact with light, but it responds to gravity. It gathered into halos long before ordinary gas fully collapsed. These halos acted like invisible basins in the fabric of space, collecting hydrogen and helium from their surroundings. The gas, still primitive and metal-free, began drifting toward these gravitational wells. As hydrogen accumulated, pressure increased, temperature rose. Yet collapse was not guaranteed. Thermal motion resisted compression. Radiation pressure pushed outward. Only in the densest halos could gravity overcome these counterforces. The balance was delicate. Too little mass, and the gas would remain diffuse. Too much expansion, and matter would disperse. But in certain regions, the threshold was crossed. Clouds of hydrogen began contracting more rapidly. Their cores grew hotter as gravitational energy converted into heat. With no heavy elements to aid cooling, the gas had to reach extreme scales before instability set in. These were not modest clouds like those that form stars today. They were vast, hundreds of thousands of times the mass of the sun. Inside them, the struggle intensified. Gravity compressed matter toward a central point. Collisions between particles increased. Temperatures climbed into the millions of degrees. The physics governing nuclear fusion waited for one final condition: enough density and heat to force hydrogen nuclei close enough to overcome their electrostatic repulsion. For hundreds of millions of years, this moment had not existed anywhere in the universe. Now, in the heart of a collapsing cloud, it was approaching. Gravity had not conquered the cosmos as a whole. Expansion still ruled the vast emptiness between structures. But in these isolated regions, gravity had carved out pockets of inevitability. The future of light depended on them. When gravity wins locally, it does not shout. It compresses, it concentrates. It turns diffuse possibility into focused intensity. The Dark Ages were ending not because expansion slowed, but because gravity found enough matter to resist it. And at the center of one such cloud, the conditions for the first fusion reaction were forming. the first sustained nuclear fire in a universe that had been cooling and dark for hundreds of millions of years. The next moment would not be gradual. It would be ignition. When gravity finally gained enough advantage inside one of those early dark matter halos, the collapse did not resemble the calm, dust-rich star formation we observe in the modern universe. There were no previous generations of stars to seed the cloud with heavy elements, no carbon or oxygen atoms to radiate heat efficiently, no silicate grains to help gas fragment into smaller clumps. The universe at that time was chemically simple, and that simplicity made the first collapse fundamentally different from anything that would follow. A massive cloud of hydrogen and helium began to contract under its own weight. As it shrank, gravitational energy converted into heat. The core grew hotter and denser, but because cooling mechanisms were limited, the cloud could not easily shed that heat. In modern star-forming regions, heavy elements allow gas to cool and fragment into many smaller stars. In the primordial universe, fragmentation was minimal. The cloud resisted breaking apart. This meant the first collapsing regions grew enormous. Instead of forming clusters of modest stars like our sun, the primordial gas likely condensed into one or a few extremely massive protostars. Some theoretical models suggest masses tens or even hundreds of times greater than the sun. These were not delicate beginnings. They were colossal accumulations of matter, gathering in an environment that had never before supported nuclear fusion. The core of the collapsing cloud continued to compress. Density rose to staggering levels. Temperatures climbed into the millions of degrees. At this stage, pressure pushed outward fiercely, but gravity remained stronger. The center became opaque to its own radiation, trapping energy and accelerating the rise in temperature. The universe had never experienced this threshold before. For the first time, a region of space was about to become self-luminous through sustained fusion, rather than leftover primordial radiation. The difference is profound. The cosmic microwave background was a remnant glow, fading with expansion. This would be an active source, continuously generating energy from nuclear processes. The final phase of collapse was violent on microscopic scales. Protons collided at increasing velocities. Quantum tunneling allowed some of them to overcome their mutual repulsion. When enough collisions succeeded, the first stable fusion reactions began. Hydrogen nuclei fused into helium, energy was released. Pressure surged outward from the core, counteracting gravity and halting the collapse. A star had been born. But this was not a star like the sun. It was likely immense, intensely hot, and short-lived. Its surface temperature far exceeded that of most stars today. It emitted powerful ultraviolet radiation capable of ionizing the surrounding hydrogen gas. For the first time since the early plasma epoch, the universe began to glow again, not uniformly, but from a distinct point in space. The first collapse had ended the cosmic dark ages locally. Light now had a source, and that single ignition would begin transforming the chemistry and structure of the entire cosmos. The first star was not gentle. It did not resemble our sun, nor any calm yellow star familiar to modern skies. It formed in a universe stripped of complexity, composed almost entirely of hydrogen and helium. Without heavy elements to assist cooling, the collapsing gas cloud could not fragment efficiently. Instead of producing many small stars, it produced one immense object. This star was likely enormous, perhaps dozens or even hundreds of times more massive than the Sun. Its gravity crushed its core to extreme densities. Temperatures soared far beyond those found in typical present-day stars. Fusion began rapidly and intensely, converting hydrogen into helium at a staggering rate. Mass defines destiny in stellar physics. The more massive a star, the faster it burns. Unlike red dwarfs, which sip their fuel slowly across trillions of years, this first star devoured its hydrogen with urgency. It shone with blistering brightness, radiating intense ultraviolet light into a universe that had known only darkness for hundreds of millions of years. Its radiation did not merely illuminate space, it transformed it. High-energy photons streamed outward, colliding with neutral hydrogen atoms and stripping away electrons. The surrounding gas became ionized once again, reversing part of the cooling that had defined the Dark Ages. This was the beginning of reionization, a gradual process that would change the transparency of the cosmos. The first star did not exist in a crowded sky. It likely burned alone or nearly alone in its region. There were no neighboring constellations, no background of distant galaxies. Its light expanded into a vast and mostly empty environment, carving out a bubble of ionized gas within the surrounding darkness. For the first time, the universe contained a structured source of radiation. This star was chemically pure by modern standards. It contained almost nothing heavier than helium. Its fusion processes were the first steps toward creating new elements. Within its core, nuclear reactions began building heavier nuclei, carbon, oxygen, perhaps even elements beyond. These were the first seeds of chemical complexity. But such a massive star was unstable in the long term. Its immense gravity required equally immense pressure to maintain equilibrium. Fusion provided that pressure, but the fuel would not last long. The larger the star, the shorter its life. Instead of billions of years, this first star may have lived only a few million. In cosmic terms, it was brief. Yet during that brief life, it altered everything. It injected radiation into darkness. It initiated the transformation of simple matter into richer chemistry. It marked the true beginning of the luminous universe. The first star was not just another object. It was the turning point between a cosmos defined by uniform simplicity and one capable of structure, diversity, and eventually life. Its existence was temporary. Its impact was permanent. Before the first star ignited, the universe was chemically simple in a way that is almost impossible to relate to today. There was hydrogen. There was helium. There were traces of lithium. And that was essentially everything. No oxygen to form water, no carbon to build organic molecules, no silicon to shape rocks, no iron to anchor planetary cores. The periodic table, as we know it, did not yet exist in reality. The Big Bang produced only the lightest elements. In its first few minutes, nuclear reactions fused protons and neutrons into helium nuclei, with small amounts of deuterium and lithium. But the universe expanded and cooled too quickly to build anything heavier. Fusion stalled. Chemistry froze at simplicity. For hundreds of millions of years, this composition defined existence. Without heavy elements, matter behaved differently. Gas clouds were less efficient at cooling. Star formation was more difficult. There were no solid particles, no dust grains, no complex molecules drifting through space. The cosmos was transparent, vast, and primitive. When the first star formed, It entered this chemically untouched environment. Inside its core, nuclear fusion began transforming hydrogen into helium at extraordinary temperatures and pressures. But in a massive star, fusion does not stop there. As hydrogen becomes scarce in the core, new reactions ignite. Helium fuses into carbon, carbon into oxygen, oxygen into heavier elements. Each stage builds a more complex nucleus, climbing the ladder of atomic weight. This was the first time in cosmic history that elements heavier than helium were forged. Inside that stellar furnace, carbon, the backbone of life, came into existence. Oxygen, essential for water and respiration, was created. Nitrogen, silicon, magnesium, and eventually iron formed in successive fusion cycles. The star became a factory for building blocks of planets, but these elements were trapped within its core. As long as the star remained stable, its newly created atoms stayed confined. The surrounding universe was still chemically barren. The transformation of cosmic chemistry required something more dramatic than fusion alone. It required release. Massive stars cannot sustain fusion indefinitely. Each new fusion stage requires higher temperatures and yields less energy. When iron forms in the core, fusion no longer produces net energy. The balance between gravity and pressure fails. Collapse becomes inevitable. And when collapse occurs in such a massive object, it is catastrophic. The first star would not fade quietly into a white dwarf. It would end violently, possibly as a pair instability supernova, or another extreme explosion type unique to very massive primordial stars. In that explosion, the heavy elements forged in its core would be scattered outward into surrounding space. For the first time, the universe would be enriched. Carbon and oxygen would mix with hydrogen clouds. Future stars would form in a medium no longer chemically pure. Cooling would become more efficient. Fragmentation would increase. The next generation of stars would be smaller, more numerous, and more diverse. The chemical evolution of the cosmos began with that first star's life and death. Before it, there were no rocky planets, no atmospheres rich in oxygen, no complex chemistry capable of assembling life. After it, the raw materials existed. The universe before heavy elements was simple and dark. The universe after the first star would never be simple again. The moment of ignition was not a flash visible across the universe. It was a threshold crossed deep inside a collapsing cloud of hydrogen. At the center of that immense mass, gravity had compressed matter to densities and temperatures never before achieved in cosmic history. Protons, driven together by extreme pressure, moved with such energy that quantum tunneling allowed them to overcome their mutual repulsion. For the first time, sustained nuclear fusion began. Hydrogen fused into helium. Energy was released, and balance was restored. Until that instant, gravity had dominated the collapse. Now a new force entered the equation, radiation pressure generated by fusion. The outward push of energy countered the inward pull of gravity. The core stabilized. The object stopped shrinking. A star was born. This was the first true engine of light. Unlike the fading glow of the cosmic microwave background, this light had structure. It originated from a defined location. It had a surface, a spectrum, a direction. It carved contrast into a universe that had known only diffuse brightness and then long darkness. The energy output of this first star was immense. Being far more massive than our sun, its core temperatures were higher, its fusion rates faster. It emitted intense ultraviolet radiation capable of ionizing vast regions of surrounding hydrogen. Neutral atoms lost their electrons. The darkness that had defined the cosmic dark ages began to recede locally. A bubble of ionized gas expanded outward from the star, growing as radiation streamed into space. This was not yet the full ionization of the universe, but it was the first crack in the long night. Ignition was not merely illumination, it was transformation. The radiation altered the thermal state of nearby matter. It influenced future collapse regions. It began reshaping the intergalactic medium. Energy flowed outward, interacting with hydrogen that had drifted untouched for hundreds of millions of years. And all of this came from a single object. In that era, there were no thousands of stars lighting a galaxy. There was likely one massive star, perhaps a few others forming in nearby halos, scattered across a vast cosmic expanse. Each ignition event was rare. Each one dramatically altered its environment. The first ignition marked the beginning of astrophysical feedback, the idea that stars do not merely form within the universe, but actively shape it. Radiation, winds, and eventual explosions regulate future star formation. They sculpt structure. They influence the distribution of matter. The universe was no longer passive. It had entered a phase where luminous objects would interact with and modify their surroundings. The first star did not simply shine, it changed the rules. Its lifetime would be short. Massive stars burn quickly. But during that brief existence, fusion continued relentlessly in its core, building heavier elements and flooding its region with radiation. Ignition was the turning point. After hundreds of millions of years of darkness and preparation, the cosmos now contained a self-sustaining source of energy. Light was no longer a relic of the Big Bang. It was being generated again. And from this moment onward, the universe would never return to its original simplicity. To understand what that first light meant, you have to imagine the scale of the darkness it pierced. The universe at that time was not a night sky scattered with faint stars. It was a vast, expanding ocean of hydrogen, almost perfectly black to any hypothetical observer. There were no constellations, no galaxies glowing in the distance, no diffuse band of starlight stretching across space. There was nothing to anchor perspective. And then, in one region, a star ignited. Its light did not illuminate a nearby landscape. There were no planets reflecting it, no dust clouds scattering it in brilliant colors. The surrounding medium was thin, primordial gas stretching for millions of light years. The first star shone into emptiness. Yet that emptiness was not unaffected. Ultraviolet radiation streamed outward, ionizing hydrogen atoms and carving a sphere of charged gas around the star. Within this sphere, electrons were stripped away from protons, altering the transparency and temperature of the region. Outside it, darkness remained intact. The boundary between light and untouched space became a physical frontier. For the first time, the universe had contrast. The star's radiation did more than brighten its surroundings. It heated the intergalactic medium locally, influencing how nearby gas clouds would collapse. Some regions may have been prevented from forming stars due to the intense radiation. Others were compressed by pressure waves and triggered into new collapses. Even in its isolation, the first star began shaping cosmic evolution. Visually, the scene would have been surreal. A single, brilliant point suspended in an enormous void, surrounded by a slowly expanding glow of ionized gas. No background galaxies, no distant starlight, just one immense source radiating into the dark. Its spectrum would have been dominated by extreme ultraviolet light, far hotter and bluer than the sun. The star likely shone millions of times brighter than our sun, yet its light would have felt lonely in that vast emptiness. This was the first beacon. Over time, more such stars would ignite in other halos, each one carving its own ionized bubble. Eventually, these bubbles would grow and merge, gradually ending the cosmic dark ages entirely. But at this stage, the universe was still mostly dark. The first star did not eliminate the night. It interrupted it. Light had returned, but sparsely. The existence of even one star changed the trajectory of the cosmos. It introduced feedback, chemical evolution, and radiation fields that had not existed before. It began the long process that would lead to galaxies, planets, and eventually observers capable of wondering how it all began. In the silence of the early universe, that first star was not just a source of illumination. It was the beginning of complexity, a single point of fusion, suspended in primordial darkness, altering the chemical and thermal destiny of everything that followed. The first star did not live gently, and it did not live long. Mass defines the rhythm of a star's existence, and this one was born massive beyond comparison with most stars today. The more massive a star, the greater the pressure in its core, and the faster nuclear fusion proceeds. What smaller stars stretch across billions or even trillions of years, a giant star consumes in a cosmic instant. Its core burned fiercely. Hydrogen fused into helium at extraordinary rates. As the hydrogen supply in the center diminished, helium fusion ignited. Carbon formed. Oxygen followed. Each successive stage required higher temperatures and produced less net energy. The star climbed the ladder of fusion rapidly, moving through phases that, in smaller stars, might never occur at all. There was no patience in this process. The star's immense gravity forced its core to ever greater densities. Fusion reactions intensified, generating enormous outward pressure. For a time, equilibrium held, but the heavier the elements created in the core, the less efficient fusion became. Eventually, iron formed, and iron cannot yield energy through fusion in a way that supports a star against collapse. At that moment, the balance failed. Gravity surged inward with overwhelming force. The core collapsed in a fraction of a second, compressing matter to extreme densities. Temperatures spiked, shock waves formed. And then, in an event unlike anything that had occurred before, the first supernova tore through the early universe. This was not a quiet fading. It was a violent release of accumulated energy. The explosion scattered the heavy elements forged in the core into surrounding space. Carbon, oxygen, silicon, iron. Atoms that had not existed before this star's life were hurled outward at immense velocities. The pristine hydrogen clouds of the early cosmos were enriched for the first time. The star's death was brief compared to its already short life, but its impact was profound. For the first time, the universe contained the raw materials for rocky planets. For the first time, chemistry could extend beyond the simplicity of hydrogen and helium. The explosion seeded nearby regions with complexity that would shape all future generations of stars. the first star did not survive long enough to see what it enabled. It lived intensely and ended catastrophically. But in doing so, it altered the trajectory of cosmic history. Its short and violent life marked the transition from a chemically primitive universe to one capable of forming galaxies rich in structure and eventually planets rich in possibility. The darkness had been broken by light. Now it was being transformed by death. And from the debris of that first supernova, the next chapter of the universe would begin. The death of the first star was not just the end of an object. It was the first true act of cosmic violence. Until that moment, the universe had expanded, cooled, and collapsed under gravity. It had changed gradually, but it had never exploded. When the massive core of that primordial star collapsed, the event unfolded faster than any previous transformation in cosmic history. Gravity compressed the inner layers inward at tremendous speed. The outer layers, no longer supported by pressure from fusion, followed. Within fractions of a second, densities reached extremes rivaling those inside atomic nuclei. Then the rebound began. A shockwave formed in the collapsing core, racing outward through the star's interior. As it traveled, it encountered layers of gas that had once been stable and luminous. Those layers were now torn apart by energy released in a violent surge. Neutrinos streamed outward in enormous numbers. Radiation flooded the surrounding space. The first supernova ignited the cosmos in a way nothing else had. Its brightness would have briefly outshone entire future galaxies. In a universe still largely dark, this explosion would have been the single most energetic event to date. But its significance was not only in brightness, it was in distribution. Inside that star, new elements had formed for the first time. Carbon, oxygen, magnesium, silicon, iron, forged in fusion layers stacked like shells within the stellar interior. The explosion shattered that structure and hurled those atoms into interstellar space. For the first time, the universe was chemically enriched. The pristine hydrogen and helium clouds that had drifted untouched since the Big Bang were now contaminated, in the most creative sense of the word, by heavier elements. These atoms would mix with surrounding gas, changing its cooling properties. Future star formation would proceed differently. Clouds could fragment more easily. Smaller stars could form. Complexity would accelerate. The first supernova was not merely destruction, it was fertilization. The explosion also reshaped its local environment gravitationally. Shock waves compressed nearby gas, potentially triggering the collapse of new star-forming regions. Where once there had been isolation, there was now interaction. The cycle of birth and death had begun. It is possible that the first star did not leave behind a neutron star or black hole in the way many massive stars do today. Some extremely massive primordial stars may have been completely disrupted in pair instability supernovae, leaving no remnant at all. In that case, the entire mass of the star was returned to space, redistributed into the expanding universe. Nothing remained at its center, but its influence persisted everywhere around it. The first supernova marked the moment when the universe ceased being chemically simple forever. From that point onward, each new generation of stars inherited the ashes of previous ones. Heavy elements accumulated over time. Galaxies became richer. Planets eventually became possible. The cosmos had crossed a threshold. It was no longer just hydrogen and helium drifting through darkness. It was a growing network of regions enriched by stellar death. Light and violence had entered the story permanently. And from that single explosion, the long path toward planets, oceans, atmospheres, and life began to unfold. When the first supernova scattered its newly forged elements into space, the universe crossed an invisible line. Until that moment, everything that existed was simple in composition and predictable in behavior. Hydrogen collapsed under gravity, helium drifted, dark matter shaped structure. But there was no chemistry capable of building variety, no atoms that could bond into the intricate patterns required for planets or life. With the death of the first star, complexity entered the cosmos. Carbon atoms, formed in the stellar core, began mixing with surrounding hydrogen clouds. Oxygen, silicon, and iron dispersed into the expanding interstellar medium. These heavier elements changed the physics of gas clouds dramatically. They allowed energy to radiate away more efficiently. They encouraged fragmentation during collapse. Instead of forming only massive stars, enriched gas could now form smaller ones. The second generation of stars was fundamentally different from the first. They were born in a universe no longer pristine. Their composition included traces of elements forged in earlier explosions. This enrichment altered their temperatures, their lifespans, and their stability. It allowed some stars to burn more steadily. It enabled planetary disks to form around them, disks containing dust grains and solid particles that could stick together. Dust had not existed before. Now it did. Tiny grains of carbon and silicates floated within gas clouds, clumping under electromagnetic forces. Over time, these grains would merge into larger structures. The building blocks of rocks were forming. The universe was no longer chemically flat. With each supernova, enrichment increased. Regions that had once been uniform grew more diverse. Different clouds contained different mixtures of heavy elements. Variations in composition led to variations in star formation and eventually to the possibility of planetary systems. Complexity does not emerge all at once, it accumulates. One explosion does not create Earth-like worlds, but it makes them possible in principle. A handful of supernovae increase metallicity, the fraction of matter composed of elements heavier than helium, enough for rocky planets to begin forming around stable stars. In time, carbon chemistry would flourish. Oxygen would combine with hydrogen to form water. Silicon would anchor planetary crusts. Iron would sink into cores, generating magnetic fields. None of these processes were possible before the first star lived and died. The birth of complexity is not an emotional event. It is a physical shift in available ingredients. The universe transitioned from a simple mixture to a chemically diverse environment capable of supporting layered structures. Galaxies would grow richer. Planetary systems would begin to appear. The cosmos would slowly fill with regions where matter organized into forms far more intricate than drifting gas. All of this traces back to that first ignition and explosion. Without the first star's brief life, the periodic table would remain truncated. Without its death, there would be no path toward geology, atmospheres, oceans, or biology. Complexity is not inevitable. It is cumulative, and it began with a single star burning in primordial darkness, reshaping the chemical destiny of the universe. The first star did not end the Dark Ages instantly. Its light carved out a bubble in the surrounding hydrogen. But beyond that sphere, the universe remained untouched. Darkness still dominated most of space, yet something irreversible had begun. With each new generation of stars forming from enriched gas, more ultraviolet radiation filled the cosmos. Each star ionized its surroundings, stripping electrons from hydrogen atoms and creating expanding regions of charged plasma. These ionized bubbles grew and eventually overlapped. The Dark Ages did not end with a single sunrise. They ended through gradual saturation. As more stars ignited across different halos, the universe became increasingly transparent to high-energy light. Neutral hydrogen, which had once absorbed and blocked radiation, was steadily converted back into ionized gas. This process is known as cosmic reionization. It reshaped the intergalactic medium completely. Before reionization, the universe was largely neutral and opaque to certain wavelengths. Afterward, it became more transparent, allowing light from distant objects to travel vast distances. This transformation set the stage for the observable cosmic web we detect today. Reionization was not chaotic in the sense of violent explosions everywhere. It was a large-scale phase transition driven by countless luminous sources gradually altering their environment. Each star contributed a fraction of the energy required to lift the universe out of its long darkness. The chemistry was no longer simple. The physics was no longer quiet. Feedback processes intensified. Radiation from early stars suppressed star formation in some regions while triggering it in others. Gas heated and expanded. Density contrast sharpened. The cosmic web, the network of filaments and nodes shaped by dark matter, became more pronounced as baryonic matter responded to these changes. By the time several 100 million years had passed since the Big Bang, the universe was fundamentally different from the one that had existed during the Dark Ages. It was brighter, it was structured, it was dynamic. The first star had been a solitary beacon. Now there were many. Small proto-galaxies formed, hosting clusters of new stars. Their combined radiation filled space with a diffuse ultraviolet glow. The night that once defined the cosmos had been pierced repeatedly until it no longer dominated. Reionization did not eliminate darkness entirely. Space between luminous structures remained vast and cold, but the era of absolute absence of stars was over. From this point onward, the universe would evolve through cycles of birth and death, enrichment and collapse, merger and growth. The Dark Ages became a memory encoded in the background radiation and the distribution of matter. The first star ended the night locally. The next generations ended it globally. And with the end of the Dark Ages, the cosmos entered a new epoch, one defined not by preparation, but by expansion of complexity and the gradual formation of the first true galaxies. As more stars ignited within dark matter halos, isolated pockets of light began clustering into something larger. Gravity did not stop shaping structure once the first star was born. It continued gathering matter into deeper wells, pulling gas and stars into growing concentrations. What began as scattered luminous points slowly organized into the earliest proto-galaxies. These were not majestic spiral galaxies like the Milky Way. They were small, irregular, chaotic assemblies of stars embedded in dense halos of dark matter. Their structure was unstable, constantly merging and interacting with neighboring systems. Yet within them, a new level of organization emerged. For the first time, stars were no longer alone. Clusters of second-generation stars formed within enriched gas clouds. Supernova explosions became more common. Heavy elements accumulated more rapidly. Radiation fields overlapped. The universe began to resemble something recognizable, not yet modern, but no longer primordial. The first galaxies were turbulent environments. Gas streamed along filaments of the cosmic web, feeding star formation. Collisions between small protogalaxies triggered bursts of new stellar birth. Shock waves rippled through interstellar media. Black holes born from the collapse of massive stars began forming in the centers of some early systems. These central black holes would grow over time, eventually becoming the supermassive black holes that anchor modern galaxies. But at this stage, they were seeds, gravitational anchors forming quietly amid chaotic surroundings. The transformation from isolated stars to structured galaxies marked another turning point. Galaxies provide stability on cosmic timescales. They trap gas, regulate star formation, and create environments where planetary systems can form repeatedly across billions of years. Without galaxies, stars would be too sparse and isolated to build complexity efficiently. Within the first galaxies, the cycle of stellar birth and death accelerated. Each supernova enriched the surrounding gas further. Metallicity increased. Cooling became more efficient. Stars became smaller on average and lived longer. The cosmic environment slowly shifted toward conditions capable of sustaining planetary systems. The earliest galaxies were dim by modern standards and extremely distant in time. Their light has been stretched by expansion for billions of years before reaching us. What we observe through powerful telescopes are faint glimpses, hints of these early structures at the edge of visibility. But their significance is immense. They represent the first stable ecosystems of stars. From one star in darkness, the universe advanced to clusters of light bound by gravity. The first galaxies were laboratories of evolution, places where chemistry, radiation, and gravity interacted continuously. Without them, there would be no long-term platforms for planet formation. Without them, the universe would remain scattered and simple. The formation of the first galaxies was not a dramatic event like a supernova. It was a gradual consolidation of structure. But it laid the foundation for everything that followed, including spiral galaxies, solar systems, and eventually observers capable of reconstructing this story. From isolation to structure, from one star to many. The universe was learning how to organize itself. We can trace the story of the first star through theory, simulation, and indirect observation. We can detect the cosmic microwave background. We can measure the large-scale structure of the universe. We can observe distant galaxies whose light has traveled for billions of years. But we cannot look up and see the very first star. It is gone. Not just physically extinguished, but erased by time and expansion. The universe is not only vast in space, it is vast in history. Light travels at a finite speed. When we observe distant objects, we see them as they were in the past. In principle, this allows us to look back in time. But there are limits. The earliest stars formed so far back that their light has been stretched by cosmic expansion to extreme wavelengths. What was once ultraviolet radiation has become infrared or radio waves, faint and diffuse. Even if a photon from the first star were still traveling toward us, it would be nearly impossible to isolate. It would be buried within the background glow of countless other sources that formed later. And there is another constraint. The first stars were likely rare and short-lived. They existed before large galaxies formed. They were scattered across immense distances. The probability of their light reaching us in a detectable, isolated form is extraordinarily small. By the time telescopes became capable of probing deep cosmic history, those early epochs had already been transformed by subsequent generations of stars and galaxies. We do not observe the first star directly. We infer it. We see its consequences in the chemical composition of ancient stars still burning today. Some extremely old stars contain only tiny traces of heavy elements, suggesting they formed shortly after the first supernova enriched their environment. We study patterns in the cosmic microwave background to understand the density fluctuations that allowed the first collapse. We analyze distant galaxies at the edge of observability to estimate when reionization occurred. The first star exists in the evidence it left behind. Its fingerprints are everywhere, even if its light is not. There is a deeper reason we cannot see it. The observable universe has a horizon defined by time and expansion. Regions too far away have receded beyond what their light can ever reach us. Even if countless first stars ignited in distant regions, their signals may be forever inaccessible. The universe does not preserve everything for observation. Some moments exist only as transitions. The first star belongs to that category. It was a singular ignition in a primordial epoch. It burned briefly, exploded, and seeded complexity. But it did not leave a monument in the sky. It left chemistry. It left structure. It left possibility. Modern telescopes, including those capable of detecting faint infrared signals from early galaxies, are pushing the boundary of what we can see. We may detect stars that formed shortly after the first ones. We may reconstruct the timeline of reionization more precisely, but the very first ignition will likely remain beyond direct observation. Its existence is written not in an image, but in the structure of reality itself. We do not see the first star. We exist because of it. The first star did not know it was first. It did not rise with ceremony. It did not signal the universe that something irreversible had begun. It simply formed because gravity, density, and temperature crossed a threshold. Physics took over. Fusion ignited. Light returned. And yet, in that quiet inevitability, the course of the cosmos changed forever. Before it, the universe was simple: hydrogen, helium, expansion, cooling. After it, there was chemistry. There was enrichment. There was a pathway toward planets, oceans, atmospheres, and eventually consciousness. The first star was not merely another object in space. It was the hinge between a universe that could not host complexity and one that eventually would. Everything we recognize, every atom in your body, every rock, every drop of water, traces back to stellar furnaces like that first one. Carbon in your cells was once forged in a core like its core. Oxygen you breathe was created in a fusion chain that began in stars descended from it. Iron in your blood was born in stellar collapse. The first star began that lineage. Its life was brief, its explosion violent, its light isolated in vast darkness. But its impact was cumulative. From one ignition came the first heavy elements. From those elements came new stars. From those stars came galaxies rich with structure. From those galaxies came stable systems capable of sustaining planets. And on at least one of those planets, billions of years later, Matter organized itself into something capable of asking how it all began. The universe did not start complex. It became complex. And complexity required a first step. There is something profoundly quiet about that realization. No grand design is required, no intervention, only the laws of physics operating under the right conditions. Gravity pulling, matter compressing, fusion igniting, death scattering new ingredients, repetition building diversity. The first star was not the climax of the universe's story. It was the beginning of everything that followed. Without it, there would be no galaxies like the Milky Way, no long-lived stars like the Sun, no rocky worlds orbiting stable light, no chemistry intricate enough to assemble life. The cosmos would remain vast, expanding, and chemically barren. Instead, it evolved from darkness to light. From simplicity to structure, from structure to awareness. The first star burned in a universe that had never seen one before. It did not last long, but in the immense scale of cosmic history, its brief existence made everything else possible. The night ended, and the story truly began.